Okay, good morning everyone. Let's get started. I hope you all had a good weekend. Today we're going to talk a little bit about dimensional analysis and Newton's laws. But before I start, I would like to quickly revisit the Levi-Civita symbol, or at least write down the name, because a couple of people asked me Levi-Civita symbol from last lecture. That was the epsilon ijk that was giving us +1, -1, or 0, depending on the permutation of the ijk. It exists also in higher dimensions, but for the vector product we only need the 3 dimensions ijk, because that's the only dimension in which the vector product is actually defined. And at the end I had to rush a little bit through the example of shooting the monkey. We'll revisit that today. So let's get started. So this is the outline of today's lecture. A couple of dimensional analysis, Newton's laws, frames of reference will be very important, principle of equivalence, and if you have time, at the end we'll have another example of the dimensional analysis. So some of you may have already seen and worked with dimensional analysis, but again, I'm trying to get everyone on the same speed. It's a useful method to determine the units of variables in an equation. Useful for checking the correctness of your solutions after you've done some manipulation, some algebra. And most of the physical quantities can be expressed in a combination of basic units. So dimensions and units are extremely important, and you have to be very well aware of those. Dimensions and unit are not the same, because a particular quantity can be expressed in many different kinds of units, but it has always the same dimensions. And we'll get to that in a second. Now, for example, for mass, we usually use m as dimension. Length is denoted dimension length usually as L. Time, whether you measure that in seconds, years, hours, it's always the dimension time, and the units can be quite a lot. Electric charge, Q, and temperature. Those from the US use Fahrenheit, then there are centigrade, Kelvin. All those are different units for the same dimensions. Now, talking about units, there are 7 base units that are being used. These are the ones as defined in the international system: meter, second, kilogram, ampere, Kelvin, mole, and candela, and all the other units are derived from those. The last change in there is kilogram. That happened earlier this year. It used to be a platinum-iridium cylinder held in France under probably very high protection, so no one could steal the kilogram. But that now has been reframed in the form of a natural constant, so Planck constant has now been used to define the kilogram as of May this year. So actually it's a big year for this SI units. There are prefixes that go from yocto to yotta, up from 10 to the minus 24 to 10 to the plus 24. And 2010, someone even proposed in an online survey 10 to the 27 as hella. So we'll see whether that ever goes through and gets accepted in the international system. Now, as I said, the main difference between units and dimensions is a particular quantity can be expressed in many different kinds of units, but it will always have the same dimension. One example is speed. So that can be kilometer per hour, can be miles per hour, can be meter per second, and you probably can come up with many more units for there, but it's always length over time, or short, what we've used before, and the dimensions L over T. Weight is a similar one. Kilograms, also newtons, or who knows their weights in stone and pound? One, not many, fortunately. There are better units to use than stones and pound, in my opinion, but it's, again, the dimensions of weight. This slide I have here shows a couple of examples of units and dimensions. Unit is hertz, 1 per second, so here we're in the SI units. This is the derived units, expression in the SI units, and then the dimensions as introduced before. Sometimes people come up with very, very interesting units. Does anyone know what a barn is? Yes, there's a physical unit called barn. Strange. Sorry, I don't know what just happened. Don't think it got scared by the barn, but I hope everyone can still read over there, and I hope that projector does not fail. It's 10 to the minus 28 square meters. During the Second World War and the development of the nuclear bomb, the physicists were looking for a secretive unit, and they came up with a barn to describe the cross-sectional area of an average nucleus. So it's a probability of a collision, and that actually stuck. And the barn on the nuclear term, so it's used in high energy physics. Barn is actually quite a big thing, and I think there's a saying in the US that when you shoot you can hit a barn door, or because it's just, or you would miss even a barn door if you're a lousy shooter, but the barn door is just extremely big. Now, it's a good tool, the dimensional analysis, but it also has a couple of weaknesses, and we'll go through a couple of examples here, starting with the period of the pendulum. Where do you usually start? You postulate a particular problem and you try to derive a physical relation from that. You have to figure out what units or what dimensions go in there. And the question here is, how does the period of a pendulum depend on its length? You need some initial insight and some things it could depend on. So if you look at that, we have a couple of variables we can use. Variables. That's a period P. The mass m of this dot mass at the end of the pendulum. The length of the pendulum. L, and the acceleration due to gravity. gravity G. Now, we have those variables which we think might go in there. So let's guess the form. We have the period P is some kind of constant K times mass to the A times L to the B times G to the C. We assume some kind of power law in there. And we've put in all these things. This is a dimensionless constant, which we can't figure out with that method, but for some of the initial things, it doesn't really matter. Now, if we now replace each of those parameters here in its dimensions, so period is time to the 1, and we have the mass to A, length to B, and then Earth's acceleration to C. And if we multiply that out, we get m to the A, length B plus C, and T minus 2C. So now we have all the dimensions collected here, and they basically have to somehow work out. And if we compare those terms in there, in the final one, in the period, we have no dimensions of mass. So if we look at it, A, the only way in which this dimension can disappear is if A is 0 to start with. Same with length. B plus C has to be 0. And in the last one, minus C equals 1. From that, we can easily write C equals minus 1/2. And from that follows B equals 1/2. And this gives us P equals K square root of L over G. K we didn't get. If you work it out, it's 2 pi. But there's nothing we can do about this here in the dimension analysis. But we arrived at the relationship that the period is only a function of the length and the Earth acceleration, or the acceleration in which you swing the pendulum. And with that, we can derive scaling laws and so on. We know that if we double the length of the pendulum, the period goes up by a factor of √2, and so on. So that's already quite powerful. Another example is Kepler's third law, describing how the period of a planet around a star depends on the various input parameters. The other laws, Kepler has 3 laws, Newton has 3 laws, which we'll cover later. They usually come in threes, apparently. Now, again, how does the period depend? There are the variables which we're going to use. So we're going to use the P, again, the period. The m0 as the mass of the central mass. Then small r is the radius of the orbit. and g is the gravitational constant. Gravitational constant. Now, putting that together again, as the similar example before, we just P equals some kind of dimensionless constant, M naught A, R B, G C, and we have to quickly figure out what G is. The gravitational constant in terms of the dimensions has MLT minus 2, sorry, don't need that. MLT minus 2 and L squared M, and that's M minus 1 L3, yeah, sorry, there's a 2 minus 2 missing here. M minus 1 L3 T minus 2. You get G by looking at the F equals M1 M2 G over R squared. That's the attraction, gravitational attraction between two forces, two masses. Now, if we then start writing T to the 1, the period is M to the A, L to the B, and then we get the G, dimensions of the G, M minus 1, L3, T minus 2 to the C. And if we simplify that and pull the terms together, we get A minus C, L B plus 3C, T minus 2C. So now we again compare the terms. What has to come out? We need A minus C to be 0, because the period again doesn't have any dimensions of mass. And we have B plus 3C equals 0, and minus 2C equals 1. And with that we start again from that one. We get C equals minus 1/2. Then we can work out A. A equals minus 1/2. And then we can also finally work out B equals 3/2. And with that, we can write period P equals K M naught minus 1/2, R 3/2, and G minus 1/2. And if I'm going to rewrite that a little bit, so it's really in the form Kepler postulated, P squared equals K squared, K squared over G M naught R to the 3. So this way we get Kepler's third law. On the right-hand side is described how you would get it applying Newton's laws, whether you equate the two forces, the centripetal force here on the right-hand side and the gravitational force on the left-hand side. The velocity is, and the period, 2 pi r is the circumference. So you've got the dimension length, dimension divided by the dimensions of time. Velocity, you plug that in, and with that you can basically work out that k squared equals 4 pi squared. And with that, you have Kepler's third law. The other laws, Kepler 1 is the orbit of a planet is an ellipsis with the sun at one of the two foci, and the second one is a line segment joining a planet and the sun sweeps out equal areas during equal intervals of times. You will visit that at parts of your courses over the year. Now, let's revisit the trajectory with which we finished last lecture, and which I had to rush, unfortunately, a little bit. Timing should be better today. So, a cannonball is fired up with two velocities, yx and yy, distance traveling along the x as our range r, acceleration due to gravity pointing downwards is g. Assume no air resistance, and like a few other things which we said last time, the Earth is rotating, we neglect that, and also that gravity is a function of altitude. If you kick up the cannonball fast enough, in principle it should be able to leave Earth's gravity. Might get a little bit hot on the way, but these are a couple of assumptions we put in there. Now, let's start first with what is called no use of directed length dimensions. So we're going to assume that it's just variable, or the range when the cannonball hits again the ground is our dimensionless variable, Vx to A, Vy to B, G to C, our dimensionless constants as usual. And from the dimensionality, if we look at the dimensions, we get length, that's a range in x direction, equals L over T to the A, L over T to B, and L over T squared, so that's the acceleration to C. If we compare the terms, we get A plus B plus C equals 1, and A plus B plus 2C equals 0. 3 variables, 2 equations, leaves one of the variable undefined, so we're a little bit stuck here. So we get 1 exponent undetermined. Determined. So what can we do about this? Before I go to the second example, I'll quickly revisit one step I rushed through last time. Come on. We've got the x-axis, we've got the y-axis, we've got our initial v0 making an angle theta with the x-axis, and we want to basically find out where it's hitting the ground again. So that's our r we're looking after. Now, if we look, we have here a Vx and a Vy. And looking at this, we can basically, so what we did last time, we started with vector A equals dv by dt equals constant, and did a few integrations to get to the equations of motion. But we can simplify that, or we can take an alternative route by recognizing that the gravity here is only changing the component in the y direction of the velocity and not in the x direction. So gravity is just pointing down, and with that we can rewrite the vector velocity as Vx, Vy equals cos theta sine theta v naught, and then plus the acceleration, and we have here minus g because it's pointing downwards, t. So we can basically separate out Vx and Vy, and then integration is pretty straightforward. If we integrate that with respect to time, we end up at x equals v naught cos theta t, y equals v naught sine theta t minus 1/2 g t squared. By simply treating it separately, they're not going to change in there. Now, if we solve this for t equals x over v naught cos theta, and we plug that in here to eliminate the time to get y as function of x, we end up at this tan theta x minus g over 2 v naught squared sec squared theta, x squared. And then we get that parabola, and if we plug that in for 0, when y hits y is 0 again, then we'll end up where the ball hits, or the cannonball hits the ground again. Now, this is when we treat it separately. And going back to the dimensional example, if you now look at the use of directed lengths, we have the dimensions of, so velocity in x direction now has directed dimensions, Lx over t rather than L over t, and velocity in y direction has Ly over t. And if we rewrite that, now the range has dimensions in x, Lx, equals Lx over t to the a, Ly over t to the b, and Ly over t squared to c. So that's gravitational related to the length or dimensions in y direction, velocity in y, velocity in x, and with that we basically get a equals 1, b equals 1, is 1, and c equals minus 1, and we get as range, basically that's y equals, that's when y equals 0 again, we get k Vx, Vy over g. Now that worked. We had enough equations to determine the variables, and here on the right-hand side of the figure it is basically shown. We've got Vxt, we solve that for 0, where it hits there. Of course at t0 it's 0, but we are interested in t non-equal 0. We get the time, we plug that in, and we arrive at the range when the ball hits the ground again, here 2 Vx, Vy, G. So k, our variable which we didn't know about, is 2. However, it would be too nice if that always worked, and you might have noticed that we already had to struggle a little bit in some of the examples. In the last one we had to use directed dimensions. They don't work every time. And in Kepler's law, some may have noticed, why didn't we use the mass of the orbiting body? Because then we would have had the similar problem as with the directed dimensions. We would have had something that is not really well defined in terms of the equations. Now, before we did a simple pendulum with just a string, a point mass, the length and the mass. Now we use a little bit of more complicated, a massive pendulum, a rigid pendulum, where we need the moment of inertia. So it's not just the period a function of g, l, and m, but now the period is a function of g, l, m, and I. And we'll get to the moment of inertia in one of the next lectures. The dimensions of the inertia is mass L squared mass times the length to the square. And then we have a challenge, because if we would write down the period P equals K as before, L to the A, G to the B, M to the C, inertia to the D, we can define some kind of function u equals I over ml, and that's dimensionless. And if we work out the same method as before with plugging in the exponents, we would end up at this one. We get again the L over G as square root as for the period, T equals L over G. But then we had this dimensionless function of this variable u, and the moment of inertia is somewhere stuck in there. So this is a little bit more the challenge as written here, and in general you have a function that is with independent dimensions, but then you have a function where you have some dimensionless variables that are put in there, and we would not know how to figure it out. We'll derive it that this is the period depending on the moment of inertia, but it's not always that straightforward. Now, a little bit more practical advice, and I think I've mentioned it before, is when you do and solve a question, every answer needs a unit. If you don't write explicitly the unit your answer has, you're going to lose marks in the exam. And the units are always a good way of actually double checking whether you have gone right or wrong somewhere along the way. And if you find out that you have to add kilograms and seconds, you know that this is not quite right. This reminds me, actually, I spotted a typo in this slide, in the candela, definition of candela. Does anyone spot with a quick sanity check what the mistake in there is? What's a typical physicist mistake? Any suggestions? Someone spotted it?
We've got a minus 14 on the hertz.
Yes.
The 5.4 to minus 14 hertz.
Exactly. So just common sense, you look at it, 10 to the minus 14 hertz would take quite a long time. So I got a minus in there. Sanity check would have immediately shown this can't be. Hertz is 1 per second. So you would have to wait 10 to the 14 seconds to see any of those changes. So a simple check whether the units or the sizes can be right often can help to spot mistakes. So please correct it. It's corrected already in the uploaded version, but not in your handout. Now, we get to something very, very important, Newton's laws of motion. Some of you probably know these already, Newton's laws of motion. Everybody, so N1, everybody continues in a state of rest or in uniform motion, constant velocity in a straight line unless acted upon by an external force. This is Newton 1. Newton 2, the rate of change of momentum is equal to the applied force, where the momentum is defined as product of mass and velocity, and the applied force, there's no slide, applied force F on a body is equal to its mass multiplied by its acceleration A. And Newton 3, when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. So actio equals reactio. So basically the way to write that last one is, if I look at F from 1 to 2 equals F to 1. So this has lots of consequences, and throughout the course we're going to use Newton up and down. Physics used to be quite well equipped with stuff to demonstrate, including apparently at some point the experiment about shooting a monkey or a toy that's falling. As I said, that led apparently from the stories I've heard to some chip in the wall. That's why some of the equipment was disbanded. I'm currently trying to get some of this stuff back, and since we're going to do quite a lot of collisions, I got some billiard balls. So we'll start with Newton 3, if the ball is at rest. So Newton 3, body exerts a force on a second body. The billiard ball pushes down on the table. With one force, the table pushes back. The body, the forces balance out, and there's no net force, and that's why it's not moving. Now, Newton 1 is, if I roll that, it rolls in a straight line unless acted upon by an external force. It rolls in a straight line, and at some point when it's going over the edge, gravity pulls it down, exerts a force, and then we've got the change, rate and change of momentum is equal to the applied force. So we had the gravity pulling down, and that's why the ball then went down. And we'll do a lot of collisions as part of this course. Now, another very important concept is frames of references, which we have to use. So frame of reference is an environment which is used to observe an event or the motion of a particle. And usually frames of references have an associated coordinate system. So the position of the body over time. So if the table is my x, sets my x and y axis, I've got the x-axis here, I can look and define the motion of the body over time with respect to this coordinate system. Now, we as observers are equipped with measurement tools, rulers, clocks. You could have timed how long it takes the ball to move from 0 to down there and fall, and then you can measure the position and the time of the events. Now, in classical mechanics, the time intervals between events is the same in all reference frames, so time is absolute. This is not the case when you move to relativity. We will have to use space-time frames because time is not absolute. Time is a parameter similar to our coordinate, and the speed of light is absolute there. In a reference frame in which Newton 1 is satisfied, the so-called inertial reference frame, and the laws of physics are all the same in all inertial reference frames. So we're going to use that a lot. Now, talking about inertial reference frames, a frame in which Newton's first law is satisfied, The best one is deep space, far away from any kind of force that can apply anything. You have no air resistance. Any star or any massive mass is far away. The billiard ball, if you would send it into motion out there, would just continue drift on like molecules do in intergalactic space. They just move for 10,000 and more kilometers. The Earth? Well, the Earth is not, in general, an ideal inertial reference frame. We are rotating, and there's gravity, so there's always a force acted upon us. There is a reference frame on Earth that could be counted as good inertial reference frame, is a lift in free fall, but I would not recommend that. Now, principle is relativity. Laws of physics are the same in all inertial reference frames. Quite often, even on Earth, we have quite a good reference frame. But again, it's something where you have to switch on your mind and make sure that you pay attention and be very clear what you're doing. Now, let's have a look at those two frames of reference, S and S prime. We have here X, that's our reference S, and at time equals 0, at t equals 0, we have them on top of each other. Now, the S prime moves, however, S prime has velocity v naught. Simple example is someone standing on the platform of at the train station. They are at rest. Train passes through. Someone on the train stands on the train, thinks they are also at rest, but with respect to each other, they have a certain velocity. So at t equals naught, x equals naught, and x prime equals naught. So S and S prime coincident. And when we transform it, the Galilean transformation, x prime equals x minus v naught, sorry, don't need that bracket, t. And we don't do any of the others, y equals y prime, z equals z prime. We just shift it with respect to the axis. And t equals t prime. This is important. That only is in the classical sense. Times are the same. So v prime becomes v prime equals v minus v naught. And the acceleration in S, prime is a prime equals a, because the velocity is a constant dv by dt equals a, and if we do dv prime by dt, we also then end up with the same a. And as a result, if you look at the forces, F prime, a force in the S prime frame equals the force in, sorry, not the direction, but is consistent with the principle of relativity. No, actually, it should be the vector. So that applies for everything that's lower than, much lower than the speed of light, and then special relativity, you have to do this up and down. Now, why is that important? From here on, there's basically no special frame. We can transform back and forth, and we will do that a few times, and we'll use various reference frames. Now, quickly before, that's a little bit of a sidestep. Since we've spoken about F equals m times a. This is more for your information. We have here two forces, the standard force Newton 2 and the two forces charge attraction from Coulombic force. They can be equaled. Even more surprising is you probably have done that quite often already. So in this Newton 2, m is some kind of value that is resisting the acceleration. So if you apply a force, the larger the mass, the smaller the acceleration. So this is kind of the inertial mass you're trying to accelerate with a force. But at the same time, it's a gravitational mass. If you look at the force attracting to bodies, you have a property of the body that leads to some kind of attraction. And the principle of equivalence dictates that these two masses, the mass resisting acceleration and the mass creating that force in gravity, is the same. It seems to be obvious, but it wasn't part of Newton's initial postulates. Now, with that, I would like to come to another example in the last 5 minutes of dimensional analysis that got someone apparently in some problems in 47. But I'm gonna quickly. So those is a movie from 1947. The first images were released in 1940. This is 45. First images released in 1947. This is the first testing of a nuclear weapon, codenamed Trinity, in the US as a result of the Manhattan Project. As you can imagine, it's all pretty classified at that point. The yield, how much explosive power that has, and in 47 the first images were released. There are 3 more looking at this, and a physicist, G.I. Taylor in Cambridge, professor for fluid dynamics, the story goes, looked at those images and by simple dimensional analysis was able to get an estimate for the yield, which was still classified. So some people in the US got a little bit surprised that someone not having any information was able to derive that. So they thought their information had leaked and so on. But it's basically just the images. The story is a little bit oversimplified because fluid dynamics and things like that, such extreme conditions, is a little bit difficult to derive what's going on. This is what I'm going to go through is a little bit of a simplified and oversimplified example. There are some assumptions in there that G.I. Taylor actually went through and calculated. Fluid dynamics, Navier-Stokes equation is one of the most difficult parts in physics. So you're probably not surprised that I'm not going to go into details there. So let's just look at the last one. So basically those were, you have seen the frame rate. So there was high, very, very fast frame rates. So you could actually take out particular pictures. And this was one of the pictures that was released. So what did G.I. Taylor do? Well, assumptions. If you've got a nuclear weapon, a lot of energy is released in a very, very small space. So as often, physicists assuming something like point light. So the assumptions. So energy G released in a small space. The shock wave is spherical. You can see that. That's probably quite a good assumption. And then you have got the radius as a function of time is what we're interested in. Now, what are the input factors for this radius? So r is, well, we have time. If we go longer in time, we expect the radius to scale. We have some initial energy that goes in there that's released in small space, and we have some density of the air that's being displaced. Actually, in there and in the prefactor k, there's quite a lot of physics that I'm glancing over. As I said, if you look it up on the internet, it's often given as simple examples of dimensional analysis, but the details are much, much more complicated. But here we just gonna illustrate some of the methods. So if I write that, our dimensionless constant, e to the x, rho to the y, t to the z, we can work out that the radius is our dimensions of length, m, x plus y, l, 2x minus 3y. I've already collected the terms t minus 2x plus z. And with that, we get x plus y equals 0. 2x minus 3y equals 1. And last but not least, minus 2x plus z equals 0. So this is from the mass, length, time. And if we rewrite that, we get r equals some kind of constants, e to the 1 over 5, rho minus 1 over 5, t 2 over 5. As I said, there's quite a lot of physics in there. Of physics in K, or in determining K in the end. Some people say he had a good hunch it should be roughly 1. I'm not sure whether that anywhere would count anywhere in exam. But if you rewrite that, and it turns out to be really roughly 1.0 for air, you get r to the 5 rho over t squared. And with that, you can see radius goes in quite well. Now, looking at that picture, time is given. So basically, what was released was enough to give an good educated estimate. Radius, let's just take roughly 100 meters. As physicists, you like those clear numbers. Density of air at this altitude, temperature, and so on, 1.2 kilogram per cubic meter. If you plug that in, you get roughly 8 times 10 to the 13 joule. 1 kiloton of TNT, that's the unit in which the explosive yield is usually given, is 4.184 times 10 to the 12 joule. So that ends up at around 18 kiloton TNT. And the actual yield is estimated between 18 and 22. So you can imagine that at a time when this was still highly confidential information, someone publishing something that is in the ballpark of being right rang the one or the other alarm bell in the military. But this is something also, if you have some understanding of the underlying physics, a simple estimate like this one can help to solve and come up with an answer. And with that, we'll finish for today, and I'll see you all tomorrow, I hope.